你会觉得很乱，东西很乱很乱的，因为它有各种的因素掺杂在一起，然后你不知道哪一个因素是最重要、最主要的。然后就是人家就是资产的问题，现在就是说它被太多因素干扰了，然后他们不能够分辨因素，所以他们会怎么说哈？看不出重点哦，就像你们考试这样，我不知道重点在哪里，所以它就会被 affect 哦，就会影响工作效率啊，影响工作的表现啊。你在考试还只是影响分哦，你在做工哦，你不是影响你自己吧，你还影响别人，整个社会都被影响的。嗯，哦，是这个原因呢，这样子讲啊。哦，所以说，就算你们不拿 Pure Max，以后没有关系，但是我希望你在我的课，你能够珍惜 Pure Max，把 Pure Max 活出来，就这样。再说，OK，你以后不做 Pure Max 不用紧的，没有关系的。但是我希望你把它活出来，OK 吗？可以吗？OK 啊，Yeah。Okay, so yeah, I have long time we didn't talk about Max already. I mean new Max. So since where's the last stop here? So last time we stopped at talking about the differentiability of inverse function. But to talk about differentiability of inverse function, right, we need to talk about continuity of inverse function first. Okay, when do we have inverse function? We only have inverse function when the function is injective. Okay, but when the function can be injective, it is when the function is strictly monotone. Okay, either you are strictly increasing or either you are strictly decreasing. So before we talk about strictly monotone, we talk about monotone. Okay, it's just non-decreasing, non-increasing. Okay, a function is called monotone if it is either non-decreasing or increasing. But what are we interested in? Oh, so first result we talk about this monotone function is if f is monotone, then if you apply f to this domain of f, you know what is this notation here? I scared you don't know. We didn't introduce it formally in class, but I know this is done in other courses. We didn't do it formally in class. What is this? F on df. df is the domain of f. Okay. F on the set is the image of the set. Or if you look at all domain already, this become a range where you can reach it by f. Okay, it's a range of f. Okay, I scared you don't know, but I add into the lecture notes about this notation here, the range. Okay, the range. I mean, in where abstract algebra, right? I think you guys keep talking about this, but correct no? Domain, codomain, range, pre-image. Hope so. Homomorphism, correct no? Yeah, homomorphism is a special function that satisfies the property of preserving group structure, but function is just random assignment. Okay, so homomorphism is a function, but satisfies some property. Okay, and what's the main result here? So the main result here is f is continuous if and only if fi is an integer. So if you can check that the image is an interval, then your f is continuous. Okay, you need to listen to my lecture is a very important skill. You need to listen the storyline first. Okay, listen the storyline, get the story right, and then start and write the story out. Okay, you cannot just write the story without getting the story right. Okay, I think this is good. I think when I mark your exam, I think Joshua did this very good. Okay, he got the idea right. And then in the exam, he didn't lose much detail. Yeah, I think he's one of the person that do this quite good. So very important, get the storyline first. Okay, storyline get out. Then your detail is almost there already. You just need to fill it in. Okay. Okay. Then what do we do? Then we show that a strictly monotone function is 1-to-1. Okay, very easy proof one. This one proof by contradiction. 1-to-1 says what? If fu equals to fv, u must be equal to v. But let's say it is not. Suppose for contradiction. It is not means what? You got u and v ma. Trichotomy law. U must be less than v or v must be less than u. Suppose one of them. Then says what? Say u greater than v. But your function is strictly monotone. Meaning what? Must be greater or less than, depend you are strictly increasing or strictly decreasing. Cannot be equal. Right? Strictly increasing, strictly decreasing. Okay? So in any case, you won't get equal sign. Okay, very easy, done. Okay, must be 1 to 1. But if you look from the graph, it's also obvious, right? If it's strictly increasing, 1x must only attach to 1y because it's either increasing or decreasing. Okay or not? Does it make sense? Okay. Get the idea right and then check the working. So since this is 1 to 1, right? 1 to 1 means what? There's a unique pre-image attached to an image. So you can define an inverse map. So I give you an image, then you just take the pre-image. So you can just define inverse function from the range back to the R by sending y to x. So what is y and x here? X is the thing that you apply to f, you get y. But this x is unique, right? Because it is 1 to 1. Okay, 1y can only have 1x. If y1 equals to y2, then x1 has to equal to x2. Okay, this is injectivity. Yeah. Okay, so we can define an inverse function, and then the thing we didn't prove in class is f inverse is continuous. Okay, f inverse is continuous. We didn't prove this in class. Okay, this is the one we missed last time. So why is inverse is continuous in is continuous? Why is the inverse is continuous? So we also use the similar argument. Okay, if your function, the image of your function is an interval, then it is continuous. Okay, so let's check why f inverse fi is an interval. F inverse fi is interval. Why? Why? So you start with an interval I. Okay, you want to look at whether the range of f inverse is an interval. So you look at f inverse of fi. So what is f inverse fi? I. Because f inverse f is an identity map, right? You go from I, okay, you send f across and then f inverse again. So it's an identity of I. Okay, so actually the image of f inverse is an interval. But from what we proved just now, if your image is interval, then your function is continuous. That's all. Okay, we don't need to go through the epsilon delta thing because the epsilon delta stuff is covered in the hard proof just now. When we want to prove if your image is an interval, then you have to be continuous. That one is a hard proof. You need to construct, but we skip it. Okay, we skip it, and it's not testable also. Okay, I won't ask you to do such construction. If you are interested, you can go and look why. If the image is an interval, then your function is continuous. You can try and look. It's in the which book? I think it's in the Petrovic books. I don't know. Is it Fitzpatrick? Fitzpatrick. Yeah, it's in Fitzpatrick. Okay. You can look at the book if you want to check the proof, but it's not very important. So far, okay or not? So far, I want you to know, I want you to remember one fact is, if f is strictly monotone, okay, on an interval, then the inverse is also continuous. This is what you need to remember. Proof not very important yet, but this fact you need to remember. When is f inverse invertible? If your f is strictly monotone. Okay, strictly increasing or strictly decreasing. Okay? Then f inverse is continuous. Okay. Okay, so why we do this? Because we want to talk about differentiability of f inverse. I want to talk about differentiability of f inverse. So what is differentiability? First, we are looking at the limit of a secant function. Okay, we look at the secant at the nearby point. Okay, we look at the secant at the nearby point. Remember what's the picture? What's the picture in your mind when we talk about differentiability? What's the picture in your mind? What's the picture in your mind? You have a graph and then you draw secant with the nearby point. Right. So let me see. Okay, something like this. So if you want to look at the tangent line, okay, we call it tangent line at P, then we look at the limit of the secant with the at P with the nearby point. Okay. Can you see or not? This P here, okay, with nearby point. Nearby point. The nearby point is getting closer and closer to P. Okay, the nearby point is getting closer to P. Make sense? Okay. So you see, from two directions, they get their limit to the same tangent line. Their limit to the same tangent line from two directions. You see, from the left, from the right, they all limit to the same tangent line. And that's why the limit exists. Okay or not? No matter how you approach. Well, I think later we'll prove this fact. We will prove it. We will prove it. So we define the derivative at x by the limit of y to x, fy minus fx over y minus x. So you see here, what is this? Limit of some function. You already learned already. Midterm test you limit of a function. Limit of a function. But this function here is special. Okay, this is a secant function. Okay, does it make sense? Okay, in the normal function, you will see like how to say what do you see? What did you see in the limit of fx? What sort of example? Maybe in the tutorial, right? Limit of x to 2 and then x squared plus x minus 2 like that. Okay. But this function here is special. It's fy minus fx over y minus x. So amongst y and x here, which one is fixed? Which variable is fixed? Y or x is fixed here? Fixed here. Okay. So you need to fix a point. Maybe x equals to 2. Then here become 2. Then here become f2. So meaning I give you a function, then you need to sub x equals to 2 to get this f2. And then fy and y is variable. And so meaning you have fy minus f, a constant here, over y minus a constant. So you are comparing what? Comparing the y values and the x value. The difference in y and the difference in x. Okay. So they are like, you are divide two functions, you know, fy and y, two functions. So this is the special of derivative, but the idea is really the limit of a function. Okay, if it exists, then we call it a derivative of f at x. Okay. But we can have an equivalent definition here. Okay, we can have equivalent definition here, where we remove the y. How we remove the y? I just look at the difference. What is y? Y are the nearby points. So how can I describe this nearby point? It must be some distance from x. Okay, maybe x plus h when h is positive. If h is positive, maybe this point is x minus h also on the left-hand side or on the right-hand side. Right? But anyhow, we just compute fx plus h minus fx over h. So y minus x become a distance h. And then this distance have to be going to be smaller, smaller, and smaller because y approach x. Okay, so this h have to approach 0. Okay, so why I introduced this equivalent definition because sometimes this might be easier to calculate. Okay, so I put down a proof here. You can have a look. Okay, how to go between these two. So how to go between these two is quite obvious, right? Quite obvious. You need to you need to relate. You need to relate y minus x to h. That's all. What the proof I put down here is a sequence proof. You can also do a epsilon delta proof if you like, because limit can be defined using epsilon delta. You can use epsilon delta proof. If you don't care about this proof, right, you must at least care about this equivalent definition. There's no y exists here. You see, bottom there should be y minus x, but now it becomes h. You see it? You compare it. Oh, let me maybe copy this first. Then I put it here. This side better, this side. Okay, you see it? Okay, can you see a difference? Okay, so y gets substitute as x minus h. It's not just substitution, you need to go through the whole process. You can imagine y going from left of x, right of x, left, right of x. So this h is also the same. Can be positive, negative, but it has to converge to 0. You know, can get the idea right? If you get the idea right, please read through my proof. Don't understand, then we can go through it together. Okay, now it's not very hard proof. You just need to write it down in technical way. Yeah, but not very hard proof. I already put inside my lecture note for last week. I update lecture 14 and 15. Okay, please read through again. And then finally is this one. This one is a very important theorem. So it tells you when f inverse is differentiable. Okay, when you can differentiate f inverse. And what is the derivative of f inverse? So when can you differentiate f inverse? So first of all, your f have to be strictly monotone and continuous. This two condition is required for f inverse to be continuous. Then, if f is continuous on the closed interval AB and differentiable at the open interval, so this is quite important. Y close, Y open. Okay. In later year, if you're going to take topology, this is quite important. Okay, this is about concept of open. But for now, you just regard it as a remove boundary. That's fine. Okay. If it's differentiable after you remove the boundary point, okay, the 2 point at the end, the end point, then the f inverse is differentiable. Okay, where is it differentiable? It's differentiable at the open interval of fa and fb only. Only open interval fa and fb. I don't know about fa and fb exactly, but within fa and fb, it is differentiable. And the derivative is equal to the 1 over. I think this one's something wrong. Is it? I think this one's something wrong. Missing something here. What am I missing? Let me see. So it is 1 over f prime. Yeah, there's a typo here. It doesn't make sense to say f inverse of s naught because I haven't related to the derivative of f yet. So it should be f inverse of s naught. So what does this mean? What is the relation between y naught and s naught? There's a good reason why I put 0 subscript on both of them. Because these 2 points are related by f. Remember where's the Where's the domain of F inverse? It is the image of F. Image of F. Is that image of F? F of something equals to Y naught. The thing here, the X naught here, is the thing that gives you F prime X naught. Okay, so meaning what? Meaning, if you're gonna find the derivative of F inverse at Y naught, what do? Go back and find the derivative at S naught, and then take the reciprocal. Take the reciprocal. Why? Inverse is somehow like the reciprocal. Inverse. And how you write 1 over 2? What's the other way to write 1 over 2? Inverse. Hey, the inverse of the function also can work like this. Special. Special. Inverse of a function also work like this, or 1 over the derivative. So it's like you can bring the inverse out. You can think like that. But proving is not like that. Okay or not? Does it make sense? Make sense or not? Can you relate to the 2 inverse? 2 inverse is 1 over 2. Okay, so inverse of a derivative become the reciprocal. Okay. The derivative of an inverse function become the inverse of a derivative of a function. Here is what? Here is a number. So here is inverse of a number. Here is the inverse of a function. So inverse of function become an inverse of a number. But this is a special of this inverse function theorem here. Okay. Okay. But this one exists or this one exists or not? F prime S not exists because F is differentiable. Okay, but maybe could be 0. Be 0. If it is 0, then we don't have this. If it's not 0, then we have this. Because if it's 0, it's just undefined or this number going very big. Either very big or either diverge, I don't know. Okay. Should be very big. Depends. I don't know. Okay, yeah. Don't want to comment about that. But if it is non-zero, then you will have this exact number. 1 over some number. Okay. Does it make sense? Okay, I don't want to go through the proof again, but the proof really depends on the continuity of F inverse. I think last time we mentioned about that. Okay? Make sense? Okay or not? Got question or not? This is just some story to recap. I didn't mention any very technical stuff yet. Okay? Got question? If not, let's do some exercise to refresh ourselves on these derivatives. So let's compute a few derivatives. So let's see what to compute. So I give you some exercise to do now. Okay, so that you can familiarize yourself with using the formal derivative of derivative. Okay, so if C is a constant, then suppose fx equals to C for all x in R, then f prime x equals to 0 for all x in R. Okay, try and prove this using the definition. And maybe do a few more. One more you can do is for an event, prove that if fx equal to xn, then f prime x equals to nxn minus 1. These are very famous results you learn from high school, right? Okay. If you want to differentiate power of x, you just bring the power down and then power minus 1. Okay, so now we want to prove why this is true. Okay, using the formal definition. Okay, I let you work for about 10 minutes. discuss with your friend how to use the limit definition, okay, to prove it. You can try and prove it. You can try and prove it.适应呢哈，适应啊，休息一下。 So you need to get the definition out first, f prime x. And you can try and compute the limit. So what's the definition? So let us be rigorous a bit. So let's be rigorous. So what's the logical statement we want to prove here? And we want to show that for every scalar, okay, if fx equal to c for all x in R, this implies that then f prime x equals 0 for all x in R. Okay. So first, we need to fix an arbitrary c first, right? Then we also fix an arbitrary x in R because we want to show for every point in R. Then what? By the definition of f prime. What is f prime at x? Is the limit of y. You use x, huh? Use x also can. We will use 2. Okay, so let's do 2. Yeah, let's do 2 of them. And then I want to convince you they are equivalent. So at least from an example, right? I already proved it in the lecture notes. I advise you to have a look. It's quite elementary. So if x, you are looking at fx plus h minus fx over h. If you are looking at y, then it's a limit from y to x of fy plus, fy minus fx over y minus x. Okay, so let's do one of them first and then we'll do the other. Okay, right. But what? But what is x on s plus h? X plus h is where? Where is x plus h? Is what? X is a real number. X plus h, h is also a real number. So real number is closed under addition. So s plus h is also a real number. But what's the function doing? For every real number, I send you to C. So f of x plus h is just C. Fx also C because x is already a real number. H H is what? H H is just H. Nothing to do with f. So what do you get? Limit of c minus c over h becomes 0. Okay, so it's a limit of a constant function 0. Okay, so you get 0. How about on the other hand? What is y? What is y? Y is also a real number. So fy should be c. Fx is also c. C minus c over y minus x become 0 over y minus x. Becomes limit of y to x on 0. Okay. So this 0 is what? Actually 0 is what? 0 should be a 0 function on h. What should be a 0 function on y? Okay, so you can see. Okay or not? Does it make sense? Okay. Otherwise, what is the limit of a number? Doesn't make sense one. We didn't define limit of a number. Correct or not? So these are function. So I mean, you see, this is a very subtle part. 比较怎么说？subtle，比较 怎么翻译华语啊？比较 subtle，比较细小，比较细微，对不对？细微哈，比较细微哈。OK，make sense。比较细微的 part。OK，when you write f(x) equal to c for all x equal to for all x in R, how can you write this? Actually, this f is equals to a constant function. So we will write like this: f(x) is equivalent to a constant function. Like that. Correct or not? Correct. When we want to view c as a function, okay. But it is okay to write like this, or it is okay. You know why? Because if you apply f to x, it becomes a number. And then what is this number? This number have to equal to c. But when I write like this, what does it mean? Fx is a constant function. Okay, so this is so okay. So actually, I tell you a lie. So here is denote the constant function that give c. Okay, okay, does it make sense? Okay, but in exam lah, if you don't write out this, it's okay lah. But since you are learning mathematics, right? So I wish you know what is happening. Okay? We didn't talk about limit of a number. We only talk about limit on two things only. Limit of a sequence, limit of a function. So if it is not sequence, it must be a function. So what function is that? It's a constant function. Okay, we only define limit on two things for now. Sequence or function. Okay, if it is not sequence, then it must be a function. So what function is that? It's a zero constant function. Okay? Because actually starting from C here, we should put something like this already. Yeah. Anyway. Okay. Okay, good. So we got 0. Okay, so now you can tell your high school junior why is it 0. Differentiate a constant function, why you get 0. Okay. Yeah, tell them. Compute the limit. Limit, they know how to compute one. Right. But compute the limit of what kind of function? Is the secant function you need to look at. Okay, how about this one? So this is a statement for all n. Okay, statement for all n, what do you need to do? You actually need to use induction. Okay, because you need to prove for all n. Okay, all statement proof for all n, you need induction. Okay, so meaning you need to prove the base case first. So what's the base case? So base case is n equals to 1. Okay, so meaning fx equals to x need to implies f prime x equals to 1. Okay, so why is this true? F prime x equals to limit of y to x of fy minus fx over y minus x. Okay. But what does my function give? My function says that for every x in R, fx equal to x. So fy equals to y, fx equals to x. No? Y minus x is. So y minus x over y minus x is just. So it's the identity function actually. Okay, identity function. And this is just equals to 1. Not identity function, this is a constant 1 function. Okay, which is equals to. Okay. Okay. Because at every point it is 1. That's why it is 1. Okay, in general, how to prove? In general. Okay, suppose it is true for inductive hypothesis. Suppose it is true for n equals to k. Okay. So inductive step. Want to show that it is true, or we want to show that what fx of x to the k plus 1 is implies f prime x is equals to k plus 1 times x to the k. Correct or not? Okay. So what's the step required here? So f prime x of limit y to x of fy minus fx over y minus x becomes what? Because y to the k plus 1 minus x to the k plus 1 over y minus x. So how to simplify? How to simplify here? How to simplify? Can we do simplification here? Can or not? Binomials, binomial expansion. How to do binomial expansion? Y minus x times y to the k plus y to the k minus 1 times x, and then plus dot 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 plus until x to the k. Correct or not? Correct, right? Yeah. Correct or not, this one? Binomial expansion. Maybe. Maybe. Maybe then you need to prove it or prove it lemma. Lemma. What is this lemma here? Bn minus an equals to b minus a times what? The sum of what? Sum of okay, maybe don't write in that form. Just write in the usual form. So b times n minus 1 plus b n minus 2 a plus dot 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 plus until a n minus 1. Okay, so prove this. Prove this. Correct or not? Can see this example. For example, very easy one. B cubed minus a cubed. How you write this down? Equals to what? B minus a times b squared plus ba plus a squared. So generalize it, generalize it to n. Okay, prove by induction also. Prove by induction because need to true for all n. Okay, prove by induction. Induction. Okay, so this one over what? Over y minus x. Okay, what do you get? So you simply get what? You simply get what? Yk plus yk minus 1 x plus dot 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 up to x. Then you get this. But altogether, what do you get when y goes to k? All of these are continuous function. Correct or not? Just polynomial. So what do you get for all these terms? You get xk plus sk minus 1 times x plus sk minus 2 times x squared, and then dot 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 plus xk. So how many sk here? sk2. No lah, sk. sk n. Right, skn. nsk. What? No, what is the n here? What is the n here? Your power is k plus 1, right? So how many left over here? Okay, man. You see, b cube minus a cube, got how many terms here? 3. So it is k plus 1. K plus 1 of sk, which is what we want to prove. See, where's this k plus 1 sk coming out? It's actually popping out from the binomial expansion. It's not just bringing the power down and then minus 1 on the power. Okay, it's popping up from the binomial. Okay, yeah, it's popping out from the binomial. It turns out there's a way to remember it. Okay, question. Let me see. You can skip induction also. You can skip induction also. I mean, if you want to skip induction, meaning you can do this the same way every time. Yeah, can you do it the same way every time? But the first time you don't quite use binomial expansion. Maybe 2 out to infinitely many times you need it. You can use binomial expansion. Yeah. Or you mean we didn't use the inductive step, right? Sorry, inductive hypothesis. Yeah, we skip the inductive hypothesis if we use this case here. So how should we use inductive hypothesis if we want? If we want to use yeah, if we're gonna use hypothesis in sorry, if we're gonna use inductive hypothesis, what way can we consider? So this way skip inductive hypothesis. Okay, so maybe we can use a second way. So what's the second way we can do it? Consider xn plus 1 prime, right? Okay, we want to compute this derivative here. So how to relate Sn plus 1 with Sn? It is just x times xn. Right. But what did we prove? Have we proved something useful already? Have we proved something useful? Oh, not yet chain rule, not yet chain rule. But product rule, yes, product rule. So we can use product rule on these two things because why? X is a differentiable polynomial. Sn also differentiable. And then we know what's the derivative of Sn and S. Because S is the base case. Sn is the inductive hypothesis. Okay, so what do we get here? We get x prime times xn plus x times xn prime. Okay, this one is by product rule. Okay. But by best case, we know that x prime is 1. Okay. By inductive hypothesis, we know that Sn prime is n times Sn minus 1. Okay. And then this is what? Sn plus n times Sn. But what is this? This is just n plus 1 times x to the power. Also can. Okay, now in this case here, we would use the inductive hypothesis. Okay, now. So we're getting this n minus n plus 1 times Sn 2 ways. So one way we use binomial expansion, the other way we use product rule. Okay, product rule. Okay, no. Yeah, there's a lot of way to getting one solution. Okay or not? So just now, secretly just now I told the method I told you, you also can prove that, if fx equals to x to the 1 over n, then f prime of x is equals to 1 over n times x to the power 1 over n minus 1. Okay, where is this x then? For every x in the domain of n. Okay, you can also can prove this using the binomial expansion. Binomial expansion, but let me see. Let me see. Yeah, I think you use it. Okay, yeah. Yeah, a variant of yeah, the binomial expansion. Okay, try and prove this. Okay, try and prove this. I think I will include in my note later. Okay, so yeah, so one way to practice this derivative is then you go and get your calculus 1 textbook. You know, calculus textbook got this list of derivative. Prove all of them using the different derivative. Not yet the what trigger. Okay, trigger we haven't introduced, but for this polynomial you can try and show it. All right, what time is it? 1:55. Okay, maybe it's better for us to take a break now. After the break, we will do chain rule. Okay, quite important chain rule. And let's resume 205.适应很危险哦，还不要来上课。要不要啊？没有，我是讲真的，至少在我这里啊不可以这样讲，不可以这样讲，不可以这样讲，就是说怎么说哈啊啊，要努力一点。对啊，他要很不是努力一点，他要很努力，不然的话会留级的。啊，
一颗不少钱，尤其是这是5颗推荐，才能有，这样550。
这不是问题，我是想问他还要不要补啊？应该哦，还要不要补吧？
我说550，
那我是说呀，
连手语多一点口才，德国请求。
但是他还不是德国写作，他已经不
多了，
他没有德国写过，他已经
最好550一个朋友，
德国写过还 OK 啊，呀，
的话就
他已经过，他还不是德国写作。
那叫5个原则。
I don't know。
你看要人在讲啊，对，然后还有从哪国外面，他以前也有老些台面。
对呀对呀对呀，我觉得他可以回家做工了。真的啊，他不是想要开公司的。嗯。
他如果开公司，应该是
在中国，在中国，
但还有管理，
他有承认，在旁边。对呀，我觉得那些不要读书的就不要读吧，怎么这样为难？这都是父母的问题。然后你知道问题在哪里吗？逼不到孩子啊，父母来逼学校，会傻吗？我问你，他逼不到他自己的孩子啊，他来逼学校。哎，你叫我们怎样管他？是不是？对啊，你都管不了，我还管得了？那是你亲生的，关我屁事，对不对？我靠，真的是
会很辛苦，能怪别人就怪别人。
是这个东西，是这个东西，是这个东西，就是这个 point，就是这个 point，就是这个 point。 我如果父母过来要给我骂一顿还是，那校长不敢骂啊，你孩子不要管好来，还叫人家去管你孩子，把他送去监狱你才知道，好太行，中了这个父母，叫他父母来再教育一遍
不行的
啊，
那不就行了？
所以说，哦，你看以后这个孩子呢，
就是就在教育，对吃又不听，然后又怪学校，然后又
是哦，
本来
然后就这样，只有就问到底哪里可以 start to 改变
纯自己
啊？
纯欲风
什么叫纯啊？什么叫纯呢？
哦，学习的对，
怎么是全？
把一张搞成第一。
I mean，学习是一个虽然是痛苦啦，但是是蛮一个怎么讲，蛮怎么说话，应该要是一个蛮满足的事情。到那个东西过后，就是很特别啊，我感觉。
有点东西，
也难受了，是难受过后是
难受过就变，
啊，哦
难，受过，
难受过后就可以喝到蜜雪。喂，你几时打到那个蜜雪啊？
我那时候看到雨线的时候，我要去 recall 回去，
对呀、对呀、对、
看那个 Paradise，
然后
那个人坐在椅子上，桌上面有一个怪怪的东西啊，
因为关于
不是这边，我看到人那里有个蜜雪在那里哦，
知道我讲话那个东西哦，那东西本来没有蜜雪的，那个之前的版本是没有蜜雪的。
是
然后刚好有一天我在做你们的 vlog 嘛，然后我才喝了蜜雪，我感觉很开心。然后我看那边有个空位，我就准备吃，画一个蜜雪。
哎，
奇怪哦，你好像没有看过，
对啊，对，很搞笑。
是吗？对呀，这个我觉得会变成对我之前我刚才那个啊，这个调了青菜的，
不可以，他没有头发，对，也不可以带进去，也不可以，但要背上，
我也
太多了。
是一个脱表，
对，背你的时候要背不了，因为你背了啊，你不用也是用不住。对，为什么我叫你们抄进去？你知道？那你们背了没有用，不是通过我叫你们抄进去
音箱
啊？对，我抓的就是这个音箱，一点的音箱，不是你还要经过一层是背，你经过一层是背啊，那又考另外一个东西了，又要考你背，又要考你会。
别到死了，
他不是进那个水身体吗？
它有3种方式，第一个会死，第二个会死，第三个
也会死。
没有，它会活在5条悟身体。
已经活在5条悟身体。
没有，就是它如果这个5分钟啊，在5分钟之内，还有如果这个卷锁的术式啊，它是有3种方式的，然后这3种方式第一个会导致在5分钟过后遗骨会死，第二个方式也会导致5分钟过后这个遗骨也会死，第三个就导致这个遗骨会有人活着。
怎么选手不会死呢？
卷手可以那个移去别人身体。
哦，然后
为什么会？然后属于
因为
不是两个永远不在身上，因为
5分钟吧。
OK，所以为什么会有第3个状态出来？
我也不知道，因为他讲什么术多什么术式是程式的，
数了谁？
一个什么间接式，一个是直接的。
有逻辑啊，
这还没有逻辑，这样就崩无聊
啊，
这样就崩了。
来看到
是这不可惜了。
两个最爱两个字了。
看到这样
越来越烂了嘛。
看他讲圆回来啊，
圆回来啊！
这关键他不会。
这边拿刀，去见作者，拿刀去见作者，
然后你要
不可以阻止这悲剧了。
我操，
也有，最后不是。中国
会
啊，我也
会的，
我也被杀死过。
有一点可能。
是呀，谁要请示？
谁要到底是什么？
对啊，就是激情猜测这样，我也没有可能。
没有乱讲，
对，乱讲，对，不能猜测。会干掉。
会不是死了？
没有事，不会，他在
被出门
对啊，还有回来的时候。
对，一个考虑的。2个点之间可以说是。很喜欢猜我呀。
哎，我有听说，然后我们可以去开一个小碗菜，我们做大碗菜。
你的有两个碗，还有一个大碗。还有吗？大碗菜就早饭了吗？
哎，我已经找到合作方了，2420的20次的，20次学生也是打算要开。
哇，24，
你看我们的2304跟2404搞在一起。他们已经去到那个尼莱，不是？不知道你们记得吧？尼莱中间那个营地对面，我们就有吃饭，不知道有没有跟你们吃过对吧？中间不是有一个车那个卖包的、卖贵的，记得吗？记得这种。它中间有一个车卖包卖贵的，他拿了电话问他能不能在厦门开，后来厦门卖包。
哇，
我那个
啊，
平时
应该是吧？要报达标还是怎么这样子？你看啊，这个口碑就是很熟啊！你看现在人越来越熟啊。就昨天嘛，那个 Victor 是打赢，然后上面那个有人讲，just now Victor Exerson he saw me, I wanted his racket, but he say no to me。因为 Exerson 走过去把牌送给人嘛，他就拿一把回去送人，然后讲 I never had so bad feeling being turned down by a man. Please respond to me。聊这种人，怎么我一定要给你？人家给都已经很好了，还有这样多人呢？
然后 XL 就
他讲 Bro, do you think I'm your next Santa？ 因为我是圣诞老人呢，真的是现在的人真的是越来越奇葩，奇不灵。
至少还有 respond 到，
是哦，
is respond，
对哦，
讨厌 respond 到，
对，奇葩呀，我觉得这种口碑都不应该走出来。
好像我看哦，但他连那个要去跟握手，我还会直接对手
我。也是讲，我也是讲，他这么啊，他是人飞过去啊，我也是不懂，我没有注意到，然后我就看到他握手，然后又有人过来嘛，哎，我也哦，但是后来也是没有什么力量哦，呀，追不上
第二局发一点点，
啊，对，第二局发现啊，我感觉是风的问题耶，因为因为 Excel 生在那边打球也是一直 out 的啊，所以应该是那个风的问题，有一点难 control，容易 out，你一用力啊，有冷气。
冷气会吹球场的，
它不吹球场，它吹上面都会影响你啊啊气流，会影响整个气流。那个场有风的，中到天龙了，天龙，Yeah， OK OK，Hello， maybe 可能 depend 啦，可能我们多一点 overtime 嘛，maybe 啊，你们没有课不？啊，我只是3点半要走吧，你2点半就走啊？走啊，先 OK， 好。OK，so chain rule 还记得 chain rule 吗？啊，先 recall 一下。Let's recall what is chain rule. Chain rule 啊，怎样用？给一个 example，give one example. S square minus 2不够 chain rule 吧？哦，OK，可以，但是也没有很那个，是不是？因为我可以 expand 它。OK，够狠，我喜欢这个人够狠。OK，看你去 expand，给你100。OK，够狠，我记得我做过这件事情。我做过什么事情哎？我 discrete math 嘛，我考他们 x 加 y 的一个 power，然后我要你用 binomial expansion 跟我讲它的 coefficient 嘛，我不可能给你4嘛，给你4你去给我 expand 一下，不是知道了咯？我就给你35。你知道他们做了什么事吗？真的开了几面，你知道吗？开了差不多应该有3面，满满的。而且啊，对啊，你重点抓对了。他开的时候不是越写越小，越写越小，因为可以 imagine 那个 limit 啊，越来越小。OK， 好了，对了，中医的重点来了，开了就对了，错？你觉得呢？错了，太多人敲算了，明白吗？很多可能性。说呀，不能够开，要用白龙没有天人来做。OK， 说这个讲座。开到天亮。OK， 说怎么办？用 chain rule. So how to use chain rule? So actually we have to use let gx equals to x squared plus 2. So that and actually hash x equals to x to the 100. So that f is equal to what? Hash gx. And then what's chain rule? What is chain rule? F prime x by chain rule, f prime x equals to what? Chain rule 是什么？ H prime gx times g prime x. Okay. So in this case here, what is f prime gx? 100 times gx to the 99. Okay. G prime x, 2x 2x, just 2x. Okay, so gx substitute back in, you get 100 times x squared plus 2 to the 99 times 2x. So I think it's not wise to multiply them together, but we can get 200x times x squared. Okay, alright. Make sense, huh? Make sense or not? Okay, you bring the power down, okay, and then reduce the power by 1, and then you differentiate the thing inside it, where you get 2x. Alright, this is how you memorize chain rule. Do the outside one first, and then differentiate the inside one. Okay, right. But why is it true in general? Why is it true in general? So we're gonna prove it. So prove the chain rule. So what's the statement we have? Let f and g be functions defined on a domain df and dg. But this dg is a bit special. This dg should be open interval, an open interval that contain df. Okay, why do we do this? So how does this f and g are related? So if f is differentiable at s naught and g is differentiable at fs naught, then what? Then the composite function g compose f is differentiable. Okay, so this is why we require the domain of f is in the dg. Okay, am I writing the right thing? So f is going from df to some range. I think something weird here happened. This should be the range of f, right? Okay, so this part here a bit naughty. Okay, let's check whether this part here, what's going on here. I do something stupid. I think this is the range of f. This should be the range of f. Wait, let me think. Wait, don't write first. Let me think. So I guess no, the other way around. Let me do like this. I think this is correct. So your function g, okay, is defined on the open interval inside this FDF. You get what I'm doing here? So let me write down for you. Let me try write down for you. So you got a f, okay, so you start from df, and then you go to FDF, so the range, okay, and then you want to do g. So what is this? Where is this dg? Where's the domain of g? Okay, where's the domain of g? So my claim is this domain of g is some open interval, okay, living inside this range. Okay, so it is differentiable if it is differentiable is differentiable at where? You composed already, okay? So this one should be differentiable at S naught. Okay, so in that case, what is this derivative? This is exactly the chain rule. Okay? So this is the chain rule. Then you differentiate the outside first, and then you multiply with, you differentiate the inside. Okay, so how to prove this? Very easy, very direct. So you want to prove derivative, right? what do? You look at the secant function. Okay, you look at the secant function. So you straight away look at GF x minus GF S naught over x minus S naught. Okay. So what is this? This is G of Fx minus G of Fx naught over x minus x naught. Okay. But how you relate this one to above one? Relate to this two. Where you get f prime s naught? This is the limit of what? So let me write down at the side first. So what is the limit of this guy? Limit of x go to x naught such that fx minus fs naught over x minus x naught. So for now, you need to change your mindset already. You need to change your mindset. When you want to differentiate thing, you need to remember this one. This is your definition, okay? Not the power 带下来 power 减一，不是那个东西的。你一定要记得这个。OK， 一跟你讲 derivative， 去找这个 secant function。OK， then 这边的 secant function 啊 ，this one 呢 ？How about g prime of x fx naught? Limit of maybe don't use x, maybe use y to fx naught such that g y minus g of fx naught over y minus fx. Okay. So you want to get to something like this too. Okay, and then take limit. Somehow this limit, yeah, and you need to take some limit to get these two terms. But this guy here quite close, quite close to these two things. How? 哎，又来了，这个是 analysis 的 trick。无中生有 ，OK， 无中生有，把这次要生什么 ？Here， 生 fx minus fs naught。OK， 无中生有。So right, so you will get gfx minus gfx naught of fx minus fx naught times fx minus fs naught over x minus x naught. Okay, so this is what we get here. Okay, so what's anything, got any problem here or not if we do this? Any problem can occur? Sorry, anything can occur here? Any problem? Oh, if this is 0, then cannot equal. You know why we asked about this? This can be 0. Remember, when we want to compute this, what kind of limit we take? S go to S naught. It's not fx go to S naught. But when you take x go to x naught, right? Maybe sometimes fx equals to fs naught. Later I give you example. Okay, later I give you example. Maybe sometimes even though you are taking sequence from x to s naught, maybe those x will reach s naught sometimes. Fx naught, I mean, fx will reach fx naught. So maybe sometimes this term undefined. But this one never mind, because you are not looking at this kind of term. So it doesn't affect the original function actually, even though fx equals to fs naught. You get what I mean? Can you get what I mean or not? The problem here is if you split into this form, this is only true. Okay, this is only true provided fx not equals to fs. Okay. Because if you look at the original one, right, even if they're equal, that's fine. It is just 0 over s minus s naught. But here is you divide by some 0. So here is the problem. So provided fs not equal to s naught, then this is true. Okay, so what do we do here? We need to cleverly skip this problems here. We need to skip this problem. Okay. Actually, we are almost done already, right? If we take limit from x to s naught, this term, because f is differentiable as s naught, okay, this is f prime x. And then this one, if x go to x naught, do we get fx going to fs naught or not? Why? Yes, because f is continuous. So this term will converge to g prime fs naught also. But the equal sign here got problem when it is when fx is equal to x naught. Okay, so we need to go about this. So here is the technical part. So here is let me label here. So what's the technical part here? So to prevent minus fx naught equal to 0 for some f and x naught, okay, we gonna introduce a special function. Okay, we call it a auxiliary function, meaning some extra routine function a b to r. So how do we define this? If y is not equal to f naught, fx naught, then we will just get the usual secant function. The usual secant function. You can observe what I'm trying to do first before you decide. If y equals to fs naught, then it is equal to g prime fs naught. Okay, so we straight away let it equal to the derivative. We don't want to go through the step. But what's special about this function? Since g is differentiable at fs naught, what does this mean? If g is differentiable at fs naught, right? This means what? Limit of this guy go to where? Limit of this guy when y go to fs naught is equal to what? G prime fs naught. So meaning this function is continuous at fs naught. It's continuous. Continuous, right? How to show this function is continuous at fs naught? You need to check that when the limit of y going to fs naught, the function limit to the g prime fs naught. But this statement is exactly talking about g is differentiable. Okay, so since g is differentiable, hash is actually continuous at fs naught. Because what? Okay, let me just write down the fact. Because limit of y going to fx naught of gy, okay, of hy, which is equals to limit of y going to fx naught of the secant function is what? Is what? It's just g prime fx naught. Correct or not? Because g is differentiable. G is differentiable, this one is true. Correct or not? If g prime is differentiable, then for every y go to fx naught, then of this secant function is equal to g prime fx. No, see here, here. See? Okay, if it's differentiable, then you got the limit. Okay. Okay, so what? So hash is differentiable, and then And then we want to look at actually FGX, HGX. Okay, so in fact, we have more. Okay, in fact, by the composition for continuous function, okay, what do we get? Okay, so what am I looking at here? So we are actually looking at F compose GX here. Okay, so what am I doing here? So I do the same thing here. The paste, but I just replace my Y to be FX. Sorry. Hey, am I doing some stupid thing? Wait, I want to look at hash of FX. Sorry, here is FX. Here is FX. So here is FX. So Y become FX, Y become FX, Y become FX. Okay. So what is this? This function is continuous at where? Is continuous at S0. Correct or not? Is it continuous at S0? Continuous at S0, this function. Continuous at S0 or not? This one is a number. Again, nothing to check. Here, other than fx equal to fs0, okay, for different x here, this thing continuous or not? Fx should be continuous. Okay, fx is continuous. And what else? Gfx continuous. Okay, in the range. But now we want to claim it is continuous at S0. Okay, meaning what? Meaning when you take x go to x0, this term here should converge to this term. But this is what we established just now. Because when x converges to S0, fx also converges to fx0 because f is continuous. Then by differentiability here, this whole term here also converges to g prime fs0. So it's continuous at S0. Okay. 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 So what do we do here? So now is better. What do I mean by better? So just now we have this big chunk of thing, right? So instead of writing this, okay, instead of writing this, what can we do? Okay, instead of writing this, what can we do here? We can write it as f on g. Sorry, I think I have a typo in my notes. So f on fx on fx minus fx naught over x minus x naught. We can write like this now. Okay. Why can we write like this? Why is the good point to write like this? If you see, if fx not equal to fs naught, what do we have? We have exactly the term we have before. Okay, but when fx equals to fs naught, what do we have? We have g prime fs naught instead. It's not this term anymore. Okay or not? But when fx equal to fs naught, notice what? On both sides, what do you get? Actually, you get 0. 0 times f of no. Okay, so both sides you get 0. This side you also get 0. Because g of fs naught minus g of fs naught. So 0 equals to something times 0. Okay. Does it make sense? So in this case here, this is better because now we got this, which is true if fx not equals to fx naught, and it is even true if x equals to fx naught. Okay, as both sides will be just 0. You won't go through the process something divided by 0. Okay or not? Okay. So in this case here, what can this function do for us? You can now take the limit. You can now take limit already. Okay, so you can now take limit where x goes to x naught. So what do you get? The key is here. The key is here. Just now we proved that f hash s naught, f hash x is continuous at x naught. So we have the first part converge to f of s naught. And then the second part converge to what? The second. F prime s naught. But what is f h on fs naught? What is this? How do we define this? This is just g prime of f s naught. Okay, so we get the chain rule. Okay, no? Okay. Yeah. So the technical part here is why we want to pass by the undefined number. So let me give you an example just now. So let me give you one example why the auxiliary function is necessary. I give you an example. So why we need to do that extra thing? Okay. So let's look at this function here. Gx equals to x squared sine 1 over x, where x is not 0. Okay, it is 0 when s equals 0. Okay, so what do you notice here? What do you notice here? At the point x equals 0, right? What happened? G0 is just 0. Okay, G0 is 0 because we define like that. Not through this. This is 1 over 0. I don't know why is that. But we define it to be 0. Okay, so this is what our definition. But some other point also 0. You know what are those points or not? Sine of what is 0? Of course, what else? Yes, n pi. All the multiple of pi, you are 0. So meaning what? So meaning when is gx can be 0? It follows what? It follows that gx is 0 whenever x equals to 1 over n pi. You see this 1 over n pi is the point that are arbitrarily close to 0. So maybe when you take sequence close to 0, you might pass by this point 1. Okay, so that means these points x equals to 1 over n pi are arbitrarily close to s equals 0. Okay? But they are not equal to 0. But 1 over n pi is not equal to 0 for all n. Okay, no? So you might pass by some point that is equal to the value at the point you are interested in. Okay, so that's why we need to skip those points. Does it make sense? But this point doesn't affect your differentiability. You need to remember it doesn't affect. Okay, these points are outside the point you're interested in, but doesn't affect your differentiability. Okay, any questions so far? So far, any question or not? Yes. Oh, I mean, you see, what is our function here is sine 1 over x. So you need to let 1 over x equals to n pi. So it is when x equals to 1 over n pi such that sine of 1 over x is n pi. Is correct. Oh, yeah. So we do a trick here. We invert the thing inside my sine. If I don't invert, this is just a normal sine x. Okay. Then n pi is nothing close to 0. N pi diverges when n large. So if I invert n pi, something that diverges, then it converges to 0. Okay. Yeah. Okay. So what's the point here? What's the point here? What's the point here? Actually, there's some point here. So what's the point here? So really, this f, do we call f or g? This g, so actually, g is differentiable everywhere. But the derivative g prime is not continuous at 0. Okay, you can find derivative at every point. Okay, so for example, let's say let's use our usual trick. So let me put like this. So for x not equal to 0, okay, let's skip formal definition first because we haven't really defined cos and sine yet. So if I want to differentiate x sine 1 over x, how do we differentiate? Product rule. Okay, what do we get? Should we get 2x sine 1 over x? Wait, let me see. Okay, sorry, I copied the wrong. So here is x squared. So should we get 2x sine 1 over x plus cos 1 over x or not? Is this right? Check. Skipping formal definition, just differentiate it using your high school knowledge. Is this what you get? Product rule. Sorry? Do you have x squared? There's a chain rule coming in again. Right. Careful. There's a chain rule coming in. Minus. Is a minus cos? Is a minus cos? I mean, differentiate sign, you won't get negative, right? But you need to differentiate 1 over x now. Okay. Yeah. Okay. Okay. So you get this. But what is g prime at 0? What is g prime at 0? What do we have? G prime at 0. G prime at 0. So here, maybe it's good if we can use definition here. So at 0 here, how to check? I use GH minus G0 over H. Okay, so let's use this one. And what is GH here? H squared sine 1 over H. Okay, and then we define G0 to be 0. Then this one over H. And then what's the limit of H times sine over H, 1 over H? This one. Sorry? 1? Not 1. Not 1. What is this one? I think this one is learned in calculus 1. but I forgot how to check this. How to find the limit of this guy? Squeeze. But this one squeezed by 1 and -1. No, I cannot squeeze like that. How to squeeze that? Oh, yes, fun by. Right. Good. Correct. I'm a bit stupid. Okay, right. So how to squeeze this guy? How to squeeze this guy? I forget to multiply h. So you squeeze this guy by h and minus h. Okay. So our squeeze theorem says what? If the left and right converge to one value, then the middle one converge. So left and right converge to 0 when h go to 0. So the middle one should also go to 0. Okay, so the converge to 0. But if you substitute, I mean, if you look at the limit of this guy, right? What is this? Keep oscillating, actually diverge. Okay, this, yeah, diverge. I think last time we saw this example last time. X times sine 1 over x. About the removable singularity. Like, I mean, this picture, remember this picture here? This one. This picture here. Okay. Yeah, this picture. So there's no limit point you have to get. Okay, but you check that the point on that limit point is 0. Okay, so this is very special case. G is differentiable everywhere. Not a special case, but a nice example. But the derivative is not continuous. Okay. It's differentiable. Okay, you can find the value, but the G prime is not continuous as a function. Okay, so that's why we need to introduce the auxiliary. Okay or not? Actually, if you want, we can stop here, but should we continue a bit further? Let me see. Oh, someone call me. PM. Yeah. So yeah, what do we do here? We continue. Well, maybe let's continue a little bit more. Maybe we can recall again tomorrow to strengthen your knowledge. Okay, so what we have done, we have proved a product rule, sum rule, quotient rule, inverse function theorem, and then chain rule. So everything you can do in high school, I think we proved it already. Okay, what's the next thing you do with derivative? What do you use derivative for? Yeah, find the maximum and minimum. So we're gonna prove that. Why you can do that? Okay, why you can use first derivative. You differentiate. Okay, what's the motivation? Give me example. Okay, now 你要出题给我做了。Okay, 这样 how to use derivative to find maximum minimum？出一个题给我做。What? Oh, 那个 application 呢？Okay, maybe it's okay, it's good also, but can we use easier like polynomial question like that? Find the maximum and minimum of a polynomial. Tell me how to do it. I mean, give me a question. Give me, or I give you a polynomial first. S squared plus 1. Also power. Okay. Use this one. Okay. Then I fix you a domain first. Let me fix you a domain. Fix on 0, 1. Okay, how to find maximum, minimum in this case? So find maximum and minimum of that. Okay, how to find? 0, 1. How do you find? Tell me, calculus 1. Okay, differentiate. So let's differentiate. Differentiate f prime x. So what do we get? Okay, just now we computed already, right? So this is like part A, part B. Oh, if you want to go to XPM like that level, so they ask you to differentiate derivative first, and then ask you to find maximum minimum. Okay, so we differentiate already just now. So it's 200x of x squared plus 1 to 99. Okay, and then okay, so let x prime x equals to 0. And then so this means 200x times x squared plus 1 to 99 is equal to 0. So what s has to be? This implies that s is equal to 0 or I think it's just 0. Just 0. This part have to be equal to 0, then you need to go to complex number already. Okay, that one is the next sem. Next sem. Where complex analysis. But so don't have only one root in real number. Okay, so this is so you need to decide whether this one maximum, minimum, right? Okay. Then what do you do? Unplug what? Oh, plug in? Okay. So check value on x equals 0. So what is f0? F0 is 1. So maximum or minimum? Why? Oh, second derivative. Oh, next second derivative some more. Okay. So second derivative is what? Wow. Second derivative is what? You calculate. I don't want. Okay, calculate. 200 times s squared plus 1 to 99. Okay, and then plus 99 times 200. Oh, right, correct. 299 times 400. So what is that? 40400. Is it? Oh, 40600. 40600. No. 99 times 400, right? 9436嘛，9436嘛。哦，396 ，OK， betul， OK， 39600 x of x square plus x square plus 1 times 98. All the way x square, thank you. OK， 对吗？ Like this. Alright. OK, so what to do next? Sub x equals to 0. When x equals 0, then what? F prime point 0 equals to 200 plus 0. So it's 200. 200 is greater than 0. So what? So this is a minimum. So x00 is a minimum. So I mean, s equals 0 is minimum, but do you need to check boundary point or not? Boundary point? Need to check. You need to check boundary point. But s equals 0 is already one of the boundary point. S equals to 1. 2 to the power 100. Okay, 2 to the power 100 is clearly larger than 1. Okay, so 没有人可以撼动它 minimum 的位置。Yes. Okay, so this whole process, we're gonna prove it. Okay, we're gonna prove it. Maybe I don't think we want to do it today. This process is quite long. We want to prove this whole first derivative proof, second derivative test. Okay, all this. So maybe I'll tell you the story first, for tomorrow. So first, you see, there's a lot of concept introduced here. So we need to introduce what is maximum first. Okay, we want to introduce what is minimum. Okay, and local maximum, local minimum. Okay, and then we will prove first derivative proof. Okay, and then we will prove what? Local extremum theorem. Okay, when you can talk about local maximum and local minimum. And then we will prove first derivative test. Okay, this is what you did here. And tomorrow we'll have some interesting theorem to prove, which is Rolle's theorem and means value theorem. Used before, no? All you guys use it, huh? I think you should have used it before. In calculus 2, huh? In calculus 2, huh? So, for example, Rolle's, calculus 2, meh? Calculus 2 is me, oh. No, I think calculus 1, but calculus 1. Yeah. So, what is Rolle's theorem says? Rolle's theorem says that if you have 2 points, you have same value, right? Okay, there must exist some point such that the derivative is 0. Why? 玩音乐的人一定要知道。不玩音乐的人也要知道。不是人。Okay. So 如果 if you have 2 points with the same value, why there's a point with 0 derivative? Oh. Okay, so this function here must be continuous first. Okay, if not continuous, then don't know that. But must be continuous. So meaning somehow they are like connected, although maybe continuous function might not be connected. But there must exist some point the tangent line is horizontal line. Okay, let me draw the picture. I think picture works better. So you have a FA. Okay, you have a FB. Okay, and then they are the same. They are working on the same line. Okay, and then you have a graph joining them. You must have some point that has gradient 0. Okay, so meaning you must have a horizontal line as your tangent. So maybe you have one here. You have one here. Okay. Why? If when FA equals to FB, right, it can be constant. If it is constant, then every point is 0 derivative. But if it's not constant, it must somehow go up and then come down again. Because in the end, you have to come back to FB. Maybe you go out here and then come down. Or maybe you go out and then maybe like a Tesla stock, okay, go down. Okay. And then maybe you rise again because today got AI news. Okay. And then you go down again, because I have to come back to FB, man. So when you go out, go down, you pass through some extreme point, maximum or minimum point. And then this maximum minimum point, we prove that we have to prove it. The derivative is 0. Okay, in the maximum or minimum point. Okay, so the maximum minimum point will give you the derivative 0. Okay. How about mean value theorem? Mean value theorem is even general. Okay, so the case that mean value theorem looks at is maybe FA and FB is different. Okay, but there must exist a tangent line such that it is equal to this chord, or last time we called it a secant, right? Okay, secant that join FA and FB if your F is continuous. So you can see if I got this, how to prove this? Yes, we just rotate this graph horizontal. Yeah. Exactly like that. But how we do that mathematically? Okay, we look at the difference of the chord with this function. Okay, but geometrically, we are just rotating this one to flat. So mean value theorem is a generalization of Rolle's theorem. Okay. For now, I just tell you the story. Tomorrow we will gonna do the real stuff. Okay. Yeah. We even have a generalized means value theorem. Okay, but that one we will talk about it. And then we will set an assignment question on that. On the generalized mean value. Okay. Yeah, we will set a assignment question on generalized means value theorem. It's about Taylor polynomial. Okay. Hopefully tonight I will give you the I will release the assignment.